So this is a habitable zone, but there is also another problem. That has to do with the action of the tides. Here is the Earth at a distance of 1 astronomical units, and when you bring the Earth closer to the Sun, the tides that are caused by the divergence of the gravitational field and go to the third power of the distance quickly increased, and there is a dangerous radius, a so-called co-rotation radius at 0.6 astronomical units, where in about 1 billion years the spin rotation of the planet will be braked so much that it will show its one face always to the Sun and the other part always away from it. In that case, the oceans on the solar side will be evaporating and deposit as ice on the backside, which would never get any energy. And therefore, in a short time, all the oceans would vanish and there would be no life on Earth. So you have to demand that a planet live outside this co-rotation radius. Let us now look at other stars, and the stars are classified by the spectral type, and for historical reasons it is written in letters, and you remember this old riddle of Russell, "Oh, be a fine girl, kiss me." This way you can remember, or if you are a woman you say, "Oh, be a fine guy, kiss me." So this is this spectral type. It's essentially a temperature classification. O stars are very hot, 35,000 degrees, and therefore the habitable zone, which you see is a factor of 2 in radius, is far out at 400 to 800 astronomical units. The G star we have already seen, like the Sun, you have it 0.7 to 1.4, and in M stars, which are quite cool, 2,600 degrees surface temperature. This is called 0.5 spectral type, or M.5. You have here this habitable zone 0.06 to 0.12 astronomical units. Now you have to have, in order to, if you want intelligent life, you know that on Earth it took 4.6 billion years to develop intelligence. Intelligence is only around, intelligence, human type intelligence, only about 2 million years. So you have to demand a similar amount of time of development on another planet. So you see, F stars, they live only 4 billion years. The time is not enough to develop intelligence, and even less so on O stars, where they live only 1 million years. So, so these spectral types are excluded. You will not have planets in a habitable zone here which can produce intelligent life. But this doesn't matter much, because these stars are not very frequent in the universe. In the galaxy, F stars are the most frequent, with 4% of all stars. But let us now look at the co-rotation radius. And you see that, for instance, for M stars, the co-rotation radius is at 0.4 astronomical unit, but the habitable zone far inside. So if you have a planet here, it will be co-rotating, and there can be no life on it. And also on K stars, it's the same thing, yeah? But here now you have a problem, because 72% of all stars in the galaxy are M stars and 14% are K stars. So only the G stars have the conditions right, that the habitable zone is outside the co-rotation radius. Now, how big is the probability that by chance a terrestrial planet will be in the habitable zone? And for this, we have to look a little bit at star formation. You know that we live in a spiral galaxy. Here you see the nice spiral arms. Ours is a bar spiral. but one cannot see it from the outside. But it's similar to this, and you see here these very dark clouds. These are dust clouds which are associated with giant molecular clouds, and these are seeds of star formation. In the following picture, you see from the radio observation, you see in the Milky Way one of these giant molecular clouds. Here is the name of it, and here is the size. And you see from the radio lines the extent of this, and also where it's very cold here. It's a region which is extremely cold, and these cold regions by some perturbations start to collapse under their own gravity, and then when the collapse starts, it changes the radius by a factor of 1,000, and because you have conservation of angular momentum, and the little rotation, and everything rotates in the galaxy a little bit, you know, this gets strongly amplified. And because this is not homogeneous here, there is a number of clumps. This collapse is not homogeneous, so you get essentially many blobs, and most of this rotational motion is going into orbital motion of these blobs. So you get, when you form a star, you don't get one star, you get a whole star cluster. And one of these blobs then collapses to form such a thing, and because the collapse goes easily parallel to the rotation axis and is impeded perpendicular to it because of the conservation of angular momentum, you get these pancake-type accretion disks. Now here in the next picture I show you a recent photograph of the Cone Nebula which shows you such a star cluster in the process of formation. This is a Spitzer Space Telescope exposure, and these are only the brightest stars. You have hundreds of weaker stars. So you see the star formation goes on with the formation of such star clusters.